Hello, everyone, and welcome to today's webinar. I'm Rosanna Francescato, Communications Director with the Clean Coalition. We are excited today to host this webinar on a leading load management solution for microgrids and demand response. And if you're attending this webinar, you probably already know how crucial a solution like this is for deploying microgrids, which our communities need for their tremendous economic, environmental, and resilience benefits. So before we get into all that, a few quick housekeeping items. We will email everyone the webinar recording and slides within a couple of business days. Also, all of our webinars are archived on our website, clean-coalition.org, under events. If you have questions at any time during the webinar, please go ahead and type them in the question pane at the right of your screen. We'll answer as many questions as we can during the Q&A, which will follow the presentations. And if you have questions about the Clean Coalition, you can contact me at rosanna@clean-coalition.org. Now I'd like to introduce our presenters for today. Craig Lewis is a founder and executive director of the Clean Coalition. He has over 30 years of experience in the renewables, wireless, semiconductor, and banking industries. Previously VP of Government Relations at Greenvolt, he was the first to successfully navigate a solar project through California's Renewable Portfolio Standard solicitation process. And he was also the energy policy lead on Steve Wesley's 2006 California gubernatorial campaign. Craig received an MBA and MSEE from the University of Southern California and a BSEE from the University of California, Berkeley. And Logan Rosevear is an application engineer at Atom Power. He has firsthand experience in the industrial and energy industries, and at Atom Power, he creates reference designs, coordination studies, and useful tools, and conducts market research. Previously, Logan worked at Commonwealth Associates as a protection and control engineer, and at ExxonMobil, where he analyzed risks and costs at their Baton Rouge refinery. Logan has a Master's of Global Engineering from The Ohio State University, as well as a Bachelor's of Science in Electrical and Computer Engineering. He also has an active professional engineering license specializing in electrical power through the state of Michigan. And you can read more about our presenters on the event listing for this webinar on our website. We will send everyone the link to that, which will include the webinar recording and slides within a couple of business days. So now I'm going to turn it over to Craig to set the stage for today's webinar. Okay, Craig.
Great. Thank you, Rosanna. Hopefully you can see my screen at the moment. I just wanted to turn my video on for a moment so people can see who they're talking or who they're hearing from. Can you see my slides? And
you just need to go into slideshow mode, Craig.
Okay, very good. I'm going to turn the video off though to save bandwidth and whatnot at the moment. But so I'm going to be talking about monitoring communication control generically. Clean Coalition refers to that as MC squared, playing off of Einstein's famous formula for energy. Energy equals MC squared. Monitoring communication control is at the core of solar microgrids and community microgrids. And so there's 3 levels of MC squared that are required for a community microgrid. Community microgrid is where you're targeting an entire grid area, has multiple facilities that will be covered. And a solar microgrid is where you're just talking about a single facility, single customer meter. But community microgrids obviously are much more complex, and there's 3 levels of monitoring communication control to effectively realize a community microgrid. And the first level is at the grid level. You need grid isolation switches to isolate the target grid areas when the broader grid is down. Secondly, you have the customer meter level. You need to be able to turn customer meters on and off according to the customer contracts, the facility tiering, in other words, how important they are to the community and to continuing to operate the grid effectively in a broader grid outage, and then energy availability. If you got plenty of energy available, keep everybody on, right? And if people were turned off, you turn those customers back on. If your choice is either just throw solar energy away, for example, or allow it to go to a load, then of course allow it to go to a load. The third level is behind the meter level. And that is where we're talking about individual on-site circuits that need to be able to turn on and off, and also individual on-site loads that need to be able to be turned on and off or attenuated, depending on energy availability and economic opportunities. And I'm thrilled that we've got Atom Power featured on this webinar, because they'll be talking about the solutions that are really key to behind the meter level. The Clean Coalition does a lot of work in community microgrids and solar microgrids, and so for us it's really important to talk about MC squared from both, from all three levels. And it really starts with tiering your facilities and tiering your loads. So tiering facilities means there's tier 1 facilities. Those are critical facilities. Think of fire stations and emergency shelters. Those facilities cannot turn off, or they should not turn off if you don't want people to die. Tier 2 facilities, these might be banks, they might be gas stations, right? The fuel pumps at the gas station. You have to have electricity to operate those fuel pumps. There's a lot of examples of tier 2 facilities. They might be multi-unit housing, where you have a really easy opportunity to shelter a whole bunch of people in place, rather than schlepping all those people to an emergency shelter and taking up beds, right? If you got an easy place to shelter folks where they live, it's kind of like an emergency shelter. And then tier 3 facilities, they're everything else. Along the vertical axis here, we have the load tiering. So tier 1 loads, these are critical loads. They should never, ever turn off. Tier 2 loads, they're priority loads, right? You keep them on as long as you can without threatening the ability to keep your tier 1s on. And tier 3 loads are everything else. So in this chart we're looking at here, this is how you do your facility tiering and load tiering for a community microgrid. And obviously the darker green color is where you never ever want those facilities and those tier 1 facilities and tier 1 loads at those facilities to ever turn off. The light green, those are also high priority from a community standpoint. The yellows are higher priority than everything else. Everything else is in gray. So for a typical solar microgrid that the Clean Coalition designs, we basically have enough solar to net zero the site, and then we put enough energy storage in place to make sure that we can keep the tier 1 critical loads on forever. And basically, if we're talking about the Santa Barbara region of California, in fact, this data was analyzed from a community microgrid that we helped design for UCSB, University of California at Santa Barbara. And we net zeroed the target load, and then we put, for every 100 kilowatts of solar, we designed in 200 kilowatt hours of energy storage. And if you maintain that 2-to-1 ratio in this part of the world, what you get is unparalleled level of resilience. You can keep your tier 1 loads on forever, and tier 1 loads are typically about 10% of the total load. Your tier 2 loads, priority loads, those are usually about 15%. You keep those on for at least 80% of the time. And then the tier 3 loads, you keep those on for at least 25% of the time. The reason I'm showing this slide, by the way, is that you can see from the shape of this diagram that you have to be able to toggle your tier 2 loads and your tier 3 loads in order for this all to work, right? You have to have that monitoring and communication control to be able to turn your tier 2 and tier 3 loads on and off as energy is available. A really quick note here, this little red rectangle is the amount of resilience you get from a typical diesel generator design. Diesel generators are typically designed for tier 1 and tier 2 loads, and they're designed, the average diesel generator only has enough on-site fuel to keep that diesel running for 2 days. So 2 days, your lights out. And so the amount of resilience you get from a solar microgrid is tremendously multiplied compared to a diesel generator approach. And at the end of the day, the Clean Coalition designs for very significant grid outages because we think that they're coming more frequently and they're going to continue to come even more frequently. And at the end of the day, therefore, diesel generators are simply just not sufficient. And getting renewables-driven microgrids is really the way to go. So here's an example of a community microgrid. This is the Santa Barbara region. It's called the Goleta Load Pocket because the only connection to the transmission system is through this substation called the Goleta Substation. I'm circling it with my mouse. Hopefully you can see that. And the transmission route that serves this substation is this purple trace. It's 40-mile stretch, comes up from Ventura, right through the heart of, it's through a mountainous region, comes up right through the heart of fire, landslide, earthquake risk. Southern California Edison, which is the utility that serves this area, has said these lines go down, they will continue to go down, and they could be down for months at a time. Right, this region is super grid vulnerable, and to fix it, right, to have renewables-driven resilience here, we need 200 megawatts of new solar, 400 megawatt hours of new energy storage, and this is a major initiative. We call it the Goleta Load Pocket Community Microgrid, and it's a major initiative from the Clean Coalition. There's 8 66 kV feeders that come out of the Goleta substation. One of them is, the Clean Coalition would consider this a little bit more important than the others. So we've tiered the 66 kV feeders, if you will, and the tier 1 feeder is the one that serves the Santa Barbara Airport, University of California, Santa Barbara, which is the primary emergency sheltering site for all of Santa Barbara County, plus a handful of other really important critical community facilities that are kind of called out in this slide. This is a block diagram of the same thing. I just want to show you one additional feature here, and that is the fact that we're getting a 160 megawatt hour battery is already planned to be in this community microgrid footprint, and we have some additional big batteries coming in here as well. But 160 megawatt hour battery is massive and can basically provide the foundation of the community microgrid that we need for this particular initial building block of the Goleta Load Pocket Community Microgrid. I do want to just give a quick example of how grid isolation switches need to be deployed in order to have effective community microgrids. This is a photograph of the Valencia Gardens Apartments in the middle of San Francisco, Mission District of San Francisco. Super high concentration of solar, obviously. The Clean Coalition has a project to add a battery there. So this is essentially the diagram of, this is the apartment complex here. There's hundreds of meters there. They serve low income and senior residents, senior citizens, and the solar is already in place, as you saw. We are adding a battery to it, and the battery is specifically designed to increase the hosting capacity of this section of the feeder circuit. The battery is going to be front of meter, and by the way, the solar is also interconnected front of meter. In front of meters, there's hundreds of meters. Each of the units is metered separately. So if we want to turn this Valencia Gardens into a community microgrid, which it should be, right? As I mentioned, this is senior citizens and low income, very vulnerable population. You want to be able to shelter these hundreds of people in place rather than schlepping them to an emergency shelter and taking up a whole bunch of beds that should go to people that don't have an easy situation to shelter in place. But the community microgrid basically is enabled very simply by the addition of a grid isolation switch right here, which is shown in red. And obviously, if the broader grid goes down, you need to open that and make sure that the solar and the storage are working together to provide for service to at least the most critical loads at the Valencia Gardens Apartments. This is kind of getting into behind the meter now. We have a situation where what you need to be able to do is identify your critical loads, your tier 1 and your priority loads, your tier 2 loads, and you need to be able to keep those on. So this is basically a high school in Santa Barbara, San Marcos High School, that the Clean Coalition has facilitated a solar microgrid. So the solar and storage basically got added to it. Where there will be a smart critical load panel that basically keeps the tier 1 loads on forever, but will toggle the tier 2 loads. In this case, we didn't have enough money. The economics didn't support swapping out critical or smart critical load panels or smart panels like atom power panels at all of the places at all of the circuit panels that we would need to, because there's dozens of circuit panels across this high school. So we had to do it in one place, and this allows for the critical loads to be maintained 100% of the time, and the tier 2 loads to be toggled on and off as needed, depending on energy availability. We're working on another design at a large commercial and industrial facility. This is the circuit flow diagram for that. In this case, we have 5 circuit panels that lead to critical loads, and we believe that the budget will support putting in smart panels, 5 smart panels, so we can individually, every place you see the green highlights, we can put in smart panels and make sure that we can turn off all the non-critical loads. So these panels that have the smart panels that I'm indicating, the 5 of them, they have both tier 1 loads, tier 2 loads, and tier 3 loads on them. So each one of those, we need to be able to program those panels and maybe even dynamically change those settings on the fly, right? When a grid outage happens for long duration, you may change what your priorities are, and the smart panels can do that. And so we can turn individual circuits on and off through this scheme. And I'm going to let Logan is going to go real deep on those kind of issues. I'm just going to close with one final point, and that is that EV charging can be critical and economically viable. It's critical because as transportation is increasingly transitioning to electric, you want to make sure that you have at least some of your EV infrastructure behind your main meter. If you have it on a separate meter, you're screwed. If the grid goes down, that meter is turning off. So the only way you can make sure that your solar microgrid is going to be able to get electricity to those EV chargers is if they're behind the main meter. And then when I say economically viable, there are opportunities from demand response and other coming market mechanisms that will allow you to make money by having flexible demand, which essentially can be flipped over and turned into flexible supply, including if we, when we get to the ability to take electricity from the vehicles to the building, right? Vehicle to building is going to really open up the ability for EV charging to make a lot of money. And I'll just also note that the utility programs, at least in California, that are incentivizing EV charging, they are waiving demand charges for the first couple of years, but after that, right, you're taking a massive risk for infrastructure that's going to be in place for decades. So, I'm a big proponent of getting that EV charging infrastructure behind the main meter and making sure that you have control of charging up your EVs that you need to when the grid is up or down, and doing the same thing in terms of taking advantage of market opportunities that exist and are increasingly going to be available. This is a typical office profile. You have the green is weekday charging on average. This is a facility that has a 20 level 2 EV chargers, and this is kind of an average of the charging rate on across those 20 level 2 EV chargers. Green is weekdays, orange is weekends. So you obviously typical commercial facility, you get a lot more people showing up at the office on the weekdays. The only constraint on them the only natural constraint on those EV chargers is the maximum power that you can charge a vehicle at, and that is 7 kilowatts as shown here, this dotted line across the top. And so you can see there's a moment in time where on average, every single EV charging port is being used at the facility. And then this just shows that if you need to, for economic reasons, either to manage your demand charges or to make sure that people aren't charging during your peak rate periods, which are between 4 and 9 p.m. in California nowadays, you can basically implement a charging profile however you want. These are EV charging is a very flexible load. You can control it however you want to. You can shape this charging profile however you want to. And in this case, we just threw an example here. If this purple dotted line is this purple hash line is basically showing that you cap the charging at 2 kilowatts, and then you turn it off. You just prohibit people from charging during that 4 to 9 peak rate period. With that, I'm handing it over to back to Rosanna or Logan.
Perfect. Thank you, Craig. Let's see. All right. So I believe I'm showing. I will share my webcam for a minute too, just so everyone can put a face to the name. Logan Rosever, application engineer here at Atom Power in Charlotte, North Carolina. And I will start off my career in the utility industry, working on the smart grid at the grid level, and now I'm working at the end of the grid, at the edge of the grid in the distribution level behind the meter. So I will show you here what Atom Power has developed and how we can use our technology in a lot of these applications. So our goal here at Atom Power is to maximize the available energy to enable a clean tomorrow. And by doing that, we're utilizing a new technology, a new type of circuit breaker, which is a solid state circuit breaker. As most of you are aware in this, who are attending this meeting, that the world of electrification is changing. There's a collision underway. We've got places like California that are mandating moving forward, every single building must be all electric, so no more gas for heating or cooking, water. And at the same time, we're shifting to electric vehicles. So a massive increase in electrification. At the same time, we're getting rid of coal. So our baseload generation is decreasing. And what that's doing is we're going to create a more instantaneous load than has ever been experienced in history on our grid. And at the same time, with a decreased load in base generation, if we can't replace all of that with enough renewables, you're seeing in the meantime, like in California, they're building these peaker plants that are running off of natural gas. And so what that does is, even though now we're reducing our dependency on coal, we're actually increasing our dependency on natural gas, which is predicted out to 2050 to actually double our amount as it was historically, almost to what the CO2 emitted from coal was in the past. So there's kind of two choices. This isn't really an either or, it can be an and as well, but we've got to increase generation and transmission, which can be done at the generation and within the grid or in a microgrid application, and also increase the visibility of control of the loads at the edge of the grid, being hot water, lighting, electric vehicles, HVAC, any high value load. And so what that kind of looks like is, if you keep building out enough generation, that's great. You have all the power that you need, but it's extremely expensive and it takes a long time, right? And it might increase our reliance on greenhouse gases. But if we can increase the visibility and control behind the meter and manage those loads, you can flatten the curve through intelligent demand response. And you do that through a fraction of the cost of rebuilding out the entire grid. You can reduce your greenhouse gases. It can be done with the technology that we have available today. But historically, it's been hard to do because to implement it universally, as I will show you here, wasn't very clear. So how does the electricity flow from the energy sources, either through the grid or a microgrid? Could be renewable, non-renewable, but it flows into your building through your main, into a feeder, into sub panels that then go through the branch circuit breaker and out to the appliances at the end. So those appliances there are all different, right? Your lighting system, your EV charger, your hot water, they're probably not manufactured by the same company. So right now, how do you kind of manage those loads, right? So after the circuit breaker, you can put a meter and a controller, some kind of communication device, and also some type of software to view the metering and control the device, right? But almost again, all of these different devices are made by different manufacturers, so that unification is lost, and it makes it difficult to scale and have a solution. But if we look at the branch circuit breaker, every single load has to go through a circuit breaker. And those circuit breakers are everywhere, in every house, in every building, through every single neighborhood. There's thousands of them. If you look at a city, there's millions of them. And in fact, in North America alone, there's 150 million sold every year. So in the words of our CEO here at Atom Power, if you can control the circuit breaker, you can control all of power distribution. Kind of looking back at the history of the circuit breaker, it's been the same basically since the discovery of it over 100 years ago. We knew that there needed to be a way to control electricity safely and to disconnect it when it wasn't being used, and that's why the circuit breaker was invented. Everything else in the world today has gone from analog to digital, right? In the same way that we can control the data flow through the routers in your house, using a solid state circuit breaker, you can now control the electron flows through the load center and the panel in your house. So why aren't there any other solid state circuit breakers on the market? Because it's very difficult to create a new circuit breaker, right? It's a life safety device. You've got UL, you've got the NFPA, all these highly regulated environments. And they've been around for a very long time. It's a long established means and methods of how they work. So it's difficult to break into that world with a life safety device. On top of that, it's dominated by a few companies that kind of own the entire electrical industry. The ones you're probably familiar with, like Siemens, ABB, Eaton, Schneider Electric. And then to create a solid state breaker, you have to have in-depth knowledge of semiconductors, how to create a semiconductor for power that can have low losses and high fault tolerant. You also need software and control to control that semiconductor reliability and safety, have it fail safe, and then also have it extremely secure from cybersecurity events so that you can't hack into the power system. Now, there is one company that has done this, and that is Atom Power. We are the only company in the world to have a digital solid state circuit breaker, and it is fully UL listed. We actually had to work with UL to create a new definition of the 489 standard, 489I, which is the UL standard for solid state circuit breakers. Now, for the first time, power distribution has become fully digital. And this is real footage of our facility and what our panel and our breakers look like, the software that controls it. It's pretty cool stuff. So using this technology, now we are paving the way for the energy transition. And what does that mean? These are our main focus areas using this technology. Demand response, flattening the curve through load shedding, distributed energy resources by being able to put solar and energy storage, community microgrids, and electric vehicle charging, which is going to very quickly become the largest load in most homes and commercial buildings. And all of this is done through one device. So here you can kind of see on the left side, our patented power semiconductor module, silicon carbide module, and our control PCB and firmware. Putting those together inside of a multi-case circuit breaker, we have a 100 amp frame, 3-pole and 2-pole device that goes inside of our Atom panel that is controlled with our Atom Insight software. So it's 100% fully vertically integrated from the power control to the breaker to the panel and the software that controls all of it. Now, using this technology that we've already proven out today, we are branching into more markets, including EV charging, which is great for commercial, fleet, multifamily, more large scale, 3-phase applications where you'd see like a 208 volt. That's great for our panel here. Then also using that same technology, we've now shrunk it down and are coming out next year with a miniature circuit breaker that will fit in a residential commercial load center that can be used for demand response, distributed energy resources, and even in data centers. So what does our EV charging solution look like? Well, we took our Gen 3 breaker and panel with our solid state on-off control, and basically ran an extension cord out to the parking lot or parking garage where you plug your vehicle in, and all of the control is done in the panel, in the distribution network, with nothing out in the parking lot itself. So it's very simple. It's easy to do demand response and energy management directly there in the panel. It's scalable. You just add another breaker every time you want a new charger, and it's cost effective, where we've seen 50% cost savings, total cost of ownership over 5 years of the product. This EV charging solution will be released here in the next couple months, November of this year. Coming next year, we've got our miniature circuit breakers, which will directly plug into a load center, which will again allow for demand response and distributed energy resources directly in the load center with built-in Wi-Fi, no hub. It's scalable. It fits into existing homes and commercial buildings. So it doesn't have to be a new install. You can go back and retrofit, and cost effective compared to a lot of the relay and contactor additional box-based solutions that are on the market today. And so why are we doing this? Well, we want to clean tomorrow. So by using this solid state technology, we can reduce greenhouse gases. We can help utilities and co-ops save billions of dollars in peak demand offset. We can enable sustainable electrification and growth. And we can help commercial and fleets accelerate EV adoption at a lower cost, at easy scalability. Going into a little more detail now, I'll go back to our circuit breaker and how that works within the power distribution network. So how is a solid state circuit breaker different than what you'd find in a traditional circuit breaker today? A traditional circuit breaker uses protection based off of normally two components, a thermal and a magnetic. The thermal is based off of when current is flowing through the breaker, it heats up, and there's a bimetallic strip in there, and as it heats up, it'll bend that bimetal, which causes it to pop open, trip the breaker. So that's more for overload events. If you're just slightly above the rating of the circuit breaker, it's more to prevent the cable underneath the breaker from getting too hot, catching fire, and causing a thermal event. The magnetic protection is done when you have a fault and you have a huge inrush of current for that fault. There's a magnetic field around that current flow, which causes the breaker to kind of pop open. So that's how a traditional circuit breaker works. A solid state circuit breaker, there are no moving parts. So you have a power semiconductor inside of there, which is controlled through a software and control algorithm through metering and monitoring of that power flow, which gives you instantaneous control on and off, the same way a computer turns on and off, the transistor ones and zeros. As soon as you see an event that you don't want to happen, you open up that semiconductor. And so where does this compare to traditional mechanical breakers? And some of these metrics here, like endurance, since you're not actually mechanically opening and closing anything, solid state circuit breaker can have millions or tens of millions of operations under full load and not see any degradation to the equipment. Every breaker that we have UL listed is rated for 200,000 amps of fault current. It's kind of unheard of in a circuit breaker. Normally you would need a fuse to get that kind of rating. And at the same time, the let through current at 200,000 amps is less than 1,500 amps of peak let through current, which is, if you're familiar with this, incredible. It's lower than any current limiting fuse on the market today. So what that does is it limits the amount of energy that is through the breaker. So you pretty much eliminate any arc flash hazard. The incident energy after our breaker is so low that class 0 PPE is really required. It's amazing stuff. The efficiency, we have a lower RDS on across the die than using a contactor and a relay with the resistance across the contacts. The making and breaking rating are the same, but you don't have to worry about contact welding any longer because there are, again, no moving parts. And you don't have to worry about any kind of performance variability. And the best part is, as this technology is adopted, the price will continue to decline, where a traditional circuit breaker has been around for over 100 years. They have completely optimized the cost of that device. So here is our 100 amp, 480 volt, 3-phase circuit breaker. Again, fastest circuit breaker in the world, fully digital controlled on and off, 200,000 amps of interrupting rating. It's got integrated metering right in the breaker for voltage, current, power factor. It's UL listed to 489, and it's programmable. So even though it's a 100 amp frame, you can program it anywhere from 15 to 100 amps with a fully customizable time current curve. Looking inside the breaker, you can see, kind of how it works. Well, you've got the control and logic in the firmware on the control board there in the middle, down towards the bottom. This is the power semiconductor where the power flows through the breaker. You've got an air gap disconnect. So what this does is it allows you to mechanically open the breaker. If you need to do any work downstream, you can put a lock through this. So you can follow all of your NEC and NFPA lockout, tagout, safety requirements. And we've got TVS array in here for transient voltage suppression, allowing for changing on high inductive loading surging events. So some industry impacts from using a solid state circuit breaker. Again, reduction of arc flash. It's a huge safety benefit here. Remote control. So instead of having to physically go and flip the breaker switch, you can do it from a tablet, a phone, a computer. It can be controlled from some external relay. It's controllable, it's easy, and it's repeatable. It takes the place of multiple devices, where before you might have a circuit breaker and a contactor and a relay and a meter and a data and communication device, all of that you'd have to get an aggregator to come in and pull it all together for you. Now it's all in one device. And instead of having a different SKU for every single current rating breaker, you don't need to buy a 20 amp and a 50 amp and a 100 amp. You buy one device and program it to whichever protective rating you need it to be at. This is our Gen 3 of this product. So you can see this is our 100 amp silicon carbide power module, our breaker, our 3-phase 400 amp panel. And on the right side, this is our Atom Insight software, kind of giving you a brief overview, changing the time current curve, some supplemental protections for frequency, voltage, phase imbalance. You can turn it on and off from right here in the software. It's pretty fun to play around with. Another application now that we have that Gen 3 product is electric vehicle charging. When looking at electric vehicle charging in the market today, customers care about energy management, making it simple, scalable, cost-effective, low overhead, and a future-proof solution. Craig kind of talked about this. When you install this, hopefully it's around here for decades, right? So you want to make sure that it's future-proof. And in certain areas like fleets, energy management is critical, so you don't have to upgrade your infrastructure costs. dropping in a new service is very expensive. And if you can get through that with energy management, it can save you a lot of money. And so to do that, we took our 400 amp panel and got a UL listing for EV specific version of our breaker. And that allows it to communicate with a pilot signal out to these pedestals. And you've got a single or double pedestal that you put in the ground in a parking lot, or a single or double wall box that you'd put on the wall in a garage. And again, there's no smarts out here and you're exposed to the public. So there's some huge benefits there. Now that all of your smart stuff's in the building, maybe in the electrical room, away from the public, away from the weather events, vandalism, you can choose a 48 or an 80 amp. 80 amp is the highest rating for level 2 charging. And again, it's programmable. So if you want it to be less than that, it can be less than that. You can do integrated energy management directly in the panel. You've got your metering and your data and your communication. And through our cloud API, you can interface with any third-party application. And it's simple. So you don't need any additional bollards out there or extra protective equipment. It's a steel tube. If you run into it, you're probably going to dent your bumper more than damage our equipment. And if something were to, the cable gets cut for some reason, in California, you're probably not used to snowplows, but on the Northeast, we've heard many times a snowplow comes through and hits the charger. Instead of having to go out and replace the whole charger, you can just put a new cable out there. So our value proposition here for the EV charging, there's no easier way to install EV infrastructure or manage that infrastructure than using our Atom Power solution. It's cost effective, it's very scalable. Not only is the energy management within the panel, there's dynamic energy management, which allows you to connect to an IP meter of your building. So you can manage your energy of the whole building. I'll talk about that here in a minute. Also, high density, you get the full 80 amps of output if that's what you want, and less risk due to your smart high value assets being in the building as opposed to exposed to damage by a vehicle. It's easy to install. You can install a panel, you can run conduit and wire and land the wire on a terminal block. That's all you need to do to install our panels. The scalable energy management. So in this case, when you go to size equipment in a building, you're going to have an NEC connected load. That is your load calculations based on the National Electric Code. And your actual building load might never reach that connected load. As you can see here in this example, maybe the NEC says your connected load is 400 kilowatt, but your actual building load might never exceed 200. But because of this, when you put in your EV charging, you're going to be limited to only installing 100 kilowatts. But with our technology, since you can put a meter ahead of our panel and actually view the building load, it allows you to have a flexible energy management system that opens that up to the entire maximum capacity. So say you have 500 kilowatts available, and during off-peak hours, you're only using 50 kilowatts. Now you have 450 kilowatts available versus the 100 kilowatts that you would have had if you only used the National Electric Code connected load values. And again, this helps prevent costly upgrades to your infrastructure in buildings that don't need it. Here's kind of a scalable, doesn't matter what vehicle is connected. It can be anything from a small car to a delivery truck. We can deliver any amount of power up to 80 amps, and all the energy management is done there in the panel with communication to the building meter. And as you keep expanding beyond one panel, multiple panels in a building, maybe multiple buildings with panels, and they can all be aggregated together with our Atom Insight software in the cloud, so you can view your energy usage across all of your facilities. High density, 80 amp charging, 48 amp charging, and programmable to anything in between. On top of the less risk of the panel being inside the building as opposed to outside, there's also, since the power is controlled at the circuit breaker level, there's no hazardous voltage at the charger, at the pedestal or the wall box when it's not in operation. And that's big because when a vehicle's plugged in, it can't move. So the highest chance of someone running into it is when they're backing in or pulling out. And during that time, there is no voltage at the pedestal. So it's very safe. Now, switching from EV charging, now we will talk about the miniature circuit breaker, which is one of the most exciting upcoming technology, I think, that we've worked on here at Atom Power. And so what we've done is we took our Gen 3 breaker and we've the same technology, but shrunk it down into a 1-inch form factor miniature circuit breaker that can now be put in any load center or most load centers that follow the 1-inch form factor. Our residential product we're hoping to have by mid to late 22. And the reason for this is, as you can see, residential makes up 39% of energy consumption in the US, commercial 34%. That's a large amount of electricity that can be controlled at the home and in buildings. Most of that is done by a few of large, like space cooling, heating, water heating, refrigeration, those high value loads. And as we talked earlier, natural gas right now is the largest growing source of these peaker plants as our base load is going away until we can get enough solar and battery storage to take over that base load generation. So using our miniature circuit breaker, there's two areas, demand response and distributive energy resources. Together, those are known as DERMS, which I'm sure you're familiar with, Distributive Energy Resource Management System. And using our circuit breaker in a panel board, with this 1-inch form factor, we kind of discovered it should fit in 80% of homes and 70% of commercial panel boards today. And here you can see, actually, this is in our facility in Charlotte here. We've tested it in a Siemens panel, an Eaton panel, GE panel, Schneider Electric panel. And you can see on the far side there, that's our Gen 3 panel. And these right here are 20 amp breakers, and we've boiled water, toasted toast, done both at the same time, tripped the breaker. It's fun stuff to do. Kind of the reason for this is of our miniature circuit breaker, having demand response and distributive energy resource applications are now growing faster than ever. And we can enable that with just a breaker replacement in the load center. It's cost effective, cheaper than putting additional panels and contactor and relay based solutions. And it's scalable with the 1-inch form factor. All you need to do is pop out your old circuit breaker and plug in the new one. Very simple. You can have customer Wi-Fi connection, or if utility wants to run this program, they can put a mobile hotspot or something in the home that allows you to have a guaranteed secure connection, and you don't have to worry about if the homeowner changes their Wi-Fi password or gets a new router. And showing how, you might think, oh, how is just replacing a circuit breaker in the home going to make any impact? Well, yes, in one home it might not, but if you look at entire neighborhoods throughout a utility industry, you've got 70,000 homes in Zone A, 50,000 homes in Zone B, 60,000 homes in Zone C. You add all that up with just a 1 kilowatt of managed load or 2 kilowatts of managed load per home, adds up to a massive amount. So here on the right side, you can see, say your grid capacity is 800 megawatts, right? With unmanaged load, you could peak close to 900 megawatts. That means you have to build another peaker plant or put some other kind of infrastructure in, right? Well, if you manage that load, you can keep that below 700 megawatt, and now you're below that grid capacity, and you don't have to worry about any kind of additional infrastructure costs. A visual difference you can see as opposed in the home to adding an additional relay box and additional combiner box, and now it can go directly into the load center. And the payback, it makes sense. You know, this is a case study, 4,000 homes with a 200 amp service. If you just replace the EV charger, a hot water heater, and an HVAC compressor, the cost of our switches over all of those homes, you know, about $3.74 million, but the total megawatt of the distributed or the demand response opportunity comes out to about $58 per kilowatt. You know, the payback to the utility varies, but we've found that it costs about 120 kilowatts per year for savings, which means right away the utility or co-op would see about $60 a kilowatt on average by hitting these high value loads. And commercial building, you know, same as residential. You go into your load center and replace it with the solid state. Now you've got energy management, demand response. You can control lighting loads. You know, peak demand savings, energy savings with remote on-off control, built-in metering, and remote monitoring. I know that's probably a lot to talk about in a short amount of time, but it looks like we're kind of getting to the end here, so I want to leave some time for questions.
Great, thank you so much, Logan. We have a lot of questions coming in.
Okay.
Let me get into them, and if you guys want to put on your cameras, that would be great too. So Alice Sung, principal at Greenbanks Associates, asks, sounds great, love the modularity for retrofit, but what happens during a long power outage and or loss of control device, power to control device, and also security issues for any digital controls? So Logan, what would happen during a long power outage?
So is this in like if you did not have backup, like solar and battery storage for? If you don't have power, the breakers aren't going to work, but you have nothing power.
I think it's a great question. I think it's really coming from the angle of, you know, even if you have a solar microgrid there that can provide indefinite backup for the critical loads. And by the way, you know, operating these panels are critical loads, right? It's kind of, it's kind of a little nested loop there of critical loads. So I think the answer is you design to make sure that that these panels are critical loads, which means they are designed to never go out. But Logan, you know, you can't design for absolute 100% certainty. So can you talk about what happens if you have to do a black start on these panels, or if you actually are coming from a dead start?
Yeah. So if you completely lose power, when the power is restored, you know, it will go into a safe state, and then depending on what the state of the breaker was previously, it can go back into that state. But there is a slight boot up period, just a few seconds before the breaker will restore whatever it was doing previously.
I'll just summarize. The answer is that this is going to be a lot better than a normal breaker situation would be, but you know, there is still that point of 1%, right? Or there's some infinitesimally you know, probability above zero that you would have to do that. But the design, any design, the Clean Coalition has with these smart panels, like from Atom Power, are to make sure those critical loads never go out.
Yeah, and you can have it where, through third-party integrations, you could tell maybe if there's a weather event coming, or if there is, a fire or something, you could redirect energy into maybe a emergency mode where it's charging up the battery as much as it can, and it cuts off all non-critical loads, or it charges up your vehicle to a full capacity, right? So then that way, if there is an emergency event, you're as prepared as possible when that happens.
Great, thanks. So getting to some basics, several people asked about pricing. Ted Flanagan, president of EcoMotion, says, Logan, great slides. Can you please discuss the cost of an Atom panel for an average municipal building? And Tristan de Frondeville, president at Skycentrics, asked, what is the pricing? Is there a recurring fee?
So for pricing, it is kind of dependent on what the application is, how many breakers you're going to have in the panel, the 3-pole or 2-pole. So if you have a specific project that you're interested in, you can reach out to us, and we can get you a PO or a quote on a panel. And for a subscription fee, no, there's nothing required within like the Gen 3 panel. There's a gateway inside the panel that creates the interface that you interact with the web browser or with the app. For EV charging, once you set it, you can just have it do its thing in the background. It's got the energy management built into the panel itself. But if you want any kind of remote access control or remote control to change schedules and stuff remotely, you're going to need a cloud service fee to connect into the panel.
Great. Ted also asked, when do you expect the circuit breakers to be on the market?
So the Gen 3, the 480 volt, 100 amp is on the market today. The EV charger should go, we're just finalizing our UL certification right now for that, should be ready in November. And then the NEMA 1-inch form factor for the commercial and residential panels, we're aiming for later next year to have that available.
Great. And you mentioned reaching out to you for pricing. In general, how would someone engage with Atom Power on a solar microgrid design?
So you can go to our website. There are a contact me page that you can fill out your information, and it'll send us to our team. And then, as an application engineer, someone on the sales team can work with you, go over one-lines, go over your application, and make sure that our product is going to fit in the application that you're looking at.
Great. Some more basics. Susan Wayo, board member and secretary for the Center for Community Energy, asks, does it speak 15118-20 standard? I don't know what that means, but I'm hoping you do.
Is that it was a 15180?
15118-20. Maybe we need to get back to Susan on that.
Oh, that's the vehicle, the grid to communication interface. Yeah, so we are working on that. The thing is, with level 2 charging, there isn't a good communication path between the charger and the vehicle. It's a one-way communication. So for level 2 charging, the charger basically, there's a pilot signal, and it's telling the vehicle, I'm an 80 amp charger, or I'm a 40 amp charger, whatever you are, but the vehicle can't communicate back to the charger. So there's some extra interface there that needs to be implemented through the standards that aren't really on the road today. A lot of that, I think, is being done in DC, because in DC charging, you can do a CAN interface and actually communicate with the vehicle. We are looking at doing a DC charger, but that is not available yet today.
Great. Susan also asked another question I want to check with you as well. Are you working with Ohm Connect? I know you mentioned demand response, so is that something that you've engaged with them on?
With Ohm Connect, I've heard of that company.
Yeah,
Are they in Denver?
on so people can, when they get notifications, they can, you know, lower their energy use. And that's been actually really helpful in preventing some or mitigating blackouts in California. So maybe we'll leave that one for later too, but that sounds interesting.
Yeah, thanks for the heads up. I'll look at it.
Yeah, we're getting a lot more questions in, but I wanted to, Tristan DeFranville also asked, can you please review in more detail how you can use 450 amps instead of 100 amps?
450 amps. So our breaker right now is only rated to a max of 100 amps. The panel is rated to 400 amps.
Logan, I think this was on your EV slides. You showed that because of the NEC limitations, right? You couldn't necessarily get pre-approved to have all those EV chargers running full speed because of all your other.
Oh,
but
I got you. Like this here.
Yeah.
Yeah. Okay. So when you have a connected load in your building, basically what that's saying is, you know, you have an HVAC system, you've got lights, you've got equipment, you know, and all of that load has a full load rating on it. And so when you do an energy audit of your building, you look at what all those loads are and you add them up and you give them some kind of factor. They might be running this percentage of the time, right? But just because they might be running 50% of the time or something doesn't mean that they're always running 50% of the time, right? They might all be running at the same time for 50% of the day. So kind of like what you're seeing here, you might have a lot of usage between 9 and to 5, but then after that, your usage goes down. So even though your connected load is showing that it's 400 kilowatts all day long, we all know it's not, right? And it's hard to see that unless you have some kind of meter upstream. So what we can do is through a building meter here upstream in the building switchgear ahead of our panel. So our panel, we know all of the loads downstream. We know what everything is pulling, right? But we can't see ahead of the panel for the building unless we put a meter up there with a internet interface, an IP like an Ethernet port. Then you connect that Ethernet port either directly into our panel or into your local area network, and it now gives us visibility to the entire building. And with that, now that unlocks all of your system capacity by subtracting the actual building load from the maximum capacity. Like, for example, if you had a 500 kilowatt transformer or something feeding your building. Great,
thanks. I know we're a little after 12, but we have a lot of questions, so maybe we can ask a few more. Tim McDuffie of Smarter Grid Solutions asks, what communications protocols do you currently support for DERMS control of your breakers?
So the breakers themselves are all controlled within the panel through a gateway. So you can connect into the gateway. We have BACnet, Open ADR, and OCPP for charging. But really it can be, because with the Open API, you have access to the data and control. So if there is any kind of implementation that you're looking for, we could try to make it work.
Great. David Brown, Principal Distribution System Engineer for SMUD, asks, can units replace residential panel main breakers to also provide isolation during a utility power failure?
So our residential product, when it first comes out next year, is going to be limited to 40 amp maximum, which means it won't be very useful as a main. I guess you could use, for example, our current 100 amp, kind of like what we're doing here, feeding it. So like in a multifamily application, we've seen people use this as our Gen 3 panel as the main, feeding a main lug only in a residential application, and using this as metering and control and on and off to each one of the residents in the multifamily home, and then having a smaller panel, and you could control certain loads on the home. But we don't have, now we do have a single breaker enclosure if you want to use just one of our breakers as well, but we don't have anything available right now that you can just put as the main in a load center.
I'm going to add just a little bit here. David Brown does amazing work at SPUD, by the way. I'm really glad he's on the webinar. So the only thing I'm confused about the question is that each customer is going to have its own meter, and so normally the turnoff would happen at the meter, and which would happen obviously the circuit panel is on the customer side of that meter, so it wouldn't be getting any power from the grid. But how many circuits can you control in say a multi-unit housing situation, so an apartment complex, condo complex, etc., that you just described, Logan? You've got your main kind of commercial sized switch, and then how many individual circuit switch for resident going out to individual residential units could you fit into that same panel, or underneath, I guess, configured with that one commercial grade switch?
Yeah, so this commercial grade panel here can hold 14 breakers inside of it. So you could put, I mean, depending on how many are on a floor, but you could put 14 breakers, so you could feed 14 apartments, I guess, per panel.
Gotcha. So if you had something like, 50 units, then you would need, could you put multiple? Yeah, okay.
Yeah, you could have multiple panels. The limit is 14 or 400 amps of the bus bar rating. So whichever, is your limiting factor. And now with energy management, you might be able to put more on, but it just depends if the residents are okay with you switching on and off their water heater if you get too close to the bus rating.
Great. Okay. Sergey Kolokov asks, how is the coordination of tripping with classic circuit breakers installed in the same circuit carried out? And how is tripping coordinated with classic circuit breakers installed in the same circuit?
Yeah, so our breaker will always be the fastest device. It's faster than any breaker or any fuse by multiple orders of magnitude. We're in the microsecond range as opposed to the millisecond range. That's how we get such a low pass-through fault current and such a low incident energy beyond our breaker. But it does have a customizable TCC. So, as a branch device, you want it to trip first because you don't want, you want it to coordinate faster than the device upstream from it. So that's great. It'll trip first every time. To coordinate with mechanical downstream from it, you'll just need to set the time current curve above that device, which may or may not be possible depending on the ratings of the two devices. So we do have in-depth time current curves available. If you need to do a coordination study, we can help you with that.
Great. Bob O'Hagan, engineer for the Clean Coalition, asks, what types of security will prevent hacker intrusion? What happens if the RF access method is down? Can the homeowner still manage atom breakers similar to how the conventional breakers are managed today?
Yes. So as for the cybersecurity, I know that's a huge topic. I'm not on the team that's developing the cybersecurity. I know that they are taking that very seriously. As for controlling the breaker like you would today, yes, you can. You can see, there's still a mechanical device here that if you want to open it up, which if you're doing any work on the other side of the breaker, we don't recommend you using the solid state as the off. We always say you should air gap before you do any work downstream, the same way that you would lock out and tag out in a commercial setting. So you would come and flip the switch, but most operations like overloads, like say you are, plugging too much stuff in the kitchen and the breaker trips, instead of having to go find your, load center and physically switch it, you can just reset it remotely, or it can be an automatic reset because it can test the circuit to see if there's any fault conditions, or if it's just an overload, wait for it to cool down and then reclose automatically.
Great. Do you have time for a couple more?
Yeah, sure.
Thanks. Great. Russ Griffith asked, what's the typical lifetime of the solid state breakers compared to mechanical?
Great. Yeah. So the kind of talked about that with the operations. I mean, we actually can't test it enough, right? There's no degradation because it's solid state. There's no moving parts. So it can operate millions or tens of millions of times. And because it operates so quickly, you don't have that high fault current that propagates through it. So you don't have like those damaging effects. Like every time a mechanical circuit breaker sees a fault, if it's 10,000 amps or 20,000 amps or more flowing through it, that's a lot of magnetic forces that are blowing that circuit breaker apart. We don't see anything like that. So we're expecting these to last way longer than a typical circuit breaker would under any kind of stressful condition.
Awesome. We have a question for you from Craig. Can the EV circuits be attenuated versus just on or off? Individual circuit attenuation control is ideal to enable the type of EV charging limits that I highlighted in my presentation. So that's a good question.
Yeah, that's a great one. EV charging is why we were so excited to convert our Gen 3 into EV charging, is because of that reason. Just turning a device on and off isn't always the best solution. And so we are able to communicate through the pilot signal to each charger and each vehicle then, which means if there is an energy management solution, like we need to lower all the chargers, or have a VIP spot and they always get the max, or first in, first out, or we have all these different load schedules and managements that you can implement with our solution without actually just killing the charging. You can turn it down and up to anything up to 80 amps.
Awesome. Great, thank you. And well, let me get to one final one. Ron Leonard, founder of Eco NRG, says we would use it to isolate a PV when a genset is turned on, so a remote isolation of the PV from the system. The PV with possible multiple panel locations, but it would seem you could cut the breaker to them all at once remotely. Does that make sense?
Yes, they do have remote control. It depends on the system. So we actually do not have a UL rating right now for a DC system, if that's what he's asking, with a solar PV. But if it has already been inverted to AC and it, up to 100 amps, you can do any kind of remote control with that device.
Great. Well, I think we'll end there. We're a little over time, but I appreciate you sticking with us, and those of the audience who stuck with us, so thank you very much. As I mentioned, we will email everyone the webinar recording and slides within a couple of business days, probably less. We will also post the recording and slides on our website under events, where you can also find other upcoming events. So thank you very much. Thanks to our presenters, and have a great day.
Yeah, thank you for having me.